Hi, this is our presentation for our final project for algorithms. Our presentation is on leveraging Quadtrees for image compression, and I'm Roberto, and I will kick us off. We have a lot of ground to cover, so let's get with it. First, why do we care about image compression? Well, reducing the sizes of image allows us to save storage space, lower transmission costs. All of those two things put together will let us save costs, and that gives us a better user experience. There's two types of image compressions. Lossy versus lossless, as the name suggests. Lossy, you lose some information, you discard anything that's irrelevant or redundant, versus lossless, which you keep all the information. In this case, we're exploring a lossy image compression called Quadtrees. What is a quadtree? A quadtree involves dividing an image into 4 quadrants and then dividing every quadrant into more subquadrants, and keep doing that until you reach a certain stopping point, which we will talk about how to figure out what that stopping point is. And then the structure actually looks like this. It's a tree with a branching factor of 4, hence the name quadtree. How do we build a quadtree? Well, first we have to convert the image into a quadtree. This involves dividing the image. As you can see here, the image has been divided, and then we stop dividing when we reach a certain depth or when we're under a certain detail threshold. So this will be explained later, but pretty much as you can tell in these parts, there's no more divisions because the color is white all throughout, versus here where you need more detail and there are a lot more divisions. And then the second part is rebuilding the image from the quadtree itself. Let's start with dividing the image. We have 2 classes, and I think explaining these classes will help understand how to create the quadtree. Our image quadrant tree class is the actual tree itself. It holds the root node, the width and height of the original image, and the max depth at which we arrived in this quadtree. And then the nodes themselves, they have a quadrant box, which is their coordinates in the complete picture. So not relative to its parents, but like the coordinates of where it goes, in the original picture. Then the depth of where we're at right now, it's children. Whether it's a leaf node or not, this is a boolean. And then detail and color. Color is the average color of the pixels in the quadrant, and the detail is how much the color of the pixels varies with respect to the other pixels in that quadrant. Let's talk about the key part here. So we know how to divide. That's easy. You just keep dividing a quadrant into more quadrants. But when do we stop? Well, there are 2 things that will indicate us when to stop. Either when we reach the max depth of the quadtree, or when we fall under a detail threshold based on the standard deviation of the pixel color. What does max depth of the tree mean? Well, if we establish a maximum depth, then we can improve the performance, because then we won't create a very deep tree. But we also don't want to have like a very shallow tree, because then we will lose a lot of detail. So determining this was like an entire task, and I'll talk about how we did it. Then the standard deviation of pixel color. If you take the standard deviation of how much every pixel varies with respect to the other pixels in the quadrant, and that's under a certain threshold, then you know when to stop dividing. As you saw in the previous image, in here everything's white, so no more divisions were needed, and that was achieved using the standard deviation. All right, so this is our original image. Let's see how we determine the max depth which our tree should have. Well, we tried many different depths. The first one was 2. As you can tell, it was divided twice, but then there's not a lot of information retained, so you can't really make out the image. Then slowly it starts improving until it reaches a point where it no longer improves, right? Like you can really tell, but the difference between 6 and 8 is more notorious than between 8 and 10. And so we decided to keep it at 8, because the deeper the tree goes, the more time it takes to compute, so there's no need for that if there's no gain by having more depth in the tree. So we picked a depth of 8. Then the detail threshold. So after picking a depth of 8 for all of these images, we were like, all right, if the standard deviation is under 100, then stop. Well, in this case, it stopped at this point, probably before the depth of 8. Can't really make out much of the picture, but then if you start reducing it, the picture starts getting clearer. But again, just like with max depth, it doesn't get any better. So at this point, we decided to use 1, but we later improved the image quality through some means that we will explain in a second. And we actually reverted back to 10, but you'll see why. But for now, we picked 1. Okay, now I'm going to leave you with Mandeep, who will talk about building the compressed image.
Oh, Hi, my name is Mandeep and I'll be taking over the presentation from Roberto. So now, Roberto gave a great explanation about how we can divide the image, how we are using Quadtrees to split the image into four quadrants, and what information do they hold. Now let's come back to the main problem statement that we are solving here. How do we build the compressed image? How do we make sure that we can make sense of the image while compressing it? So we need less space to store the same image, but still we need to have see the relevant information. It should still look like a flower. So the leaf nodes are enough to build up the entire image. It's because the image is split into quadrants, which is further split into quadrants depending on whether it has enough detail or not. If we can combine all the leaf nodes, they will actually form up the image itself. So if we have information about the color of the leaf nodes, which is the average color that the node is holding, and the position in the image, in the main image, the position that it will hold, we can draw up the original image with more or less quality. How we can do it is we'll start with a blank slate and see what quadrants at what depth should we use to build up the compressed image. Now users can determine, they can fine tune at what level of compression they want. So for example, if they say they want a image compressed up to a level of 3, as Roberto just specified, 2 or 4, as as you see, as with the depth increases, the quality of the image increases. It's because the lower you go, the more the depth, more are the number of leaf nodes that you're combining. More leaf nodes you're combining, it means that you're averaging out less quadrants, which would mean more detail. Now comes the most important part. How do we define at which point do we have to stop splitting the coordinates? That's where the standard deviation would come into place. Now what does standard deviation tells us? It tells us how much in a collection of data points, how much the data points differ from each other. So for example, if we have an array of 2 2 2, the standard deviation would be 0 because there's not much information. It's all the same numbers. Now for example, if the array contained 2, 10, and 100, as you can see, the numbers are varying. There's much information to look into it because there are the numbers are they have a large range. Now we are using a library called Pillow Python, which is a Python imaging library, which gives us histogram details of the image. So histogram would provide the bands for RGB, the red, green, and blue bands of the image, and each of those bands would have an array of 255 elements. Now, as you have might have seen in many cases, and the color of a pixel can be on an image will have some certain RGB values. And each for each of the bands RGB, you can specify a value between 0 to 255. Now, how the Python library returns us the format is it returns us an array for each of these bands of size 255, and the value at each of those indexes would represent the number of the pixels with that particular index color intensity. So, for example, if in an array of 256 elements, the value present at the 10th index is 5. It means that 5 pixels in the image had a color of that particular index of value 10. So that we can use that to calculate a standard deviation. Now here is a formula for standard deviation. So what is our weighted average? Weighted average is the average pixel intensity color in an image. So let's say we are talking about red color first. So we'll calculate separate weighted averages for RGB first of all. So what is I here? I is the color intensity of that particular band. So 0 to 255 for RGB, I would be the color intensity, and weighted average is the average pixel intensity color for a particular band. And what is value I here? Value I represents the number of pixels that were present with the ith intensity in a particular band. So this way, what we can do is we can multiply these values and divide it by the total number of pixels and take a square root of it, which will provide us the standard deviation. That is the colors, how much the colors for a particular band differentiate in the given quadrant. And if this standard deviation value, it it is more than the threshold deviation that we have defined. That means that this image still contains a lot of detail and we need to split it. Once we keep splitting, there will come a point when the image quadrant won't have much detail, and that is the point where we decide that we have to stop splitting the image, and it contains enough information to be recombined later. Now, as we specified earlier, that we'll be calculating standard deviation for RGB bands, but we'll be using different weights for each of these bands. For red, it is 0.2989, for green, it is 0.5870, and for blue, it is 0.1140. We are using these values because it is an accepted norm that with these weights, our eyes are sensitive to these colors. So the green color is more sensitive to our eyes. So that's why it'll have the greatest weight, followed by red, followed by blue, and multiplying these numbers with the standard deviations, we'll get the final standard deviation, which will be used to decide whether to split further or not. As you can see, with their improved standard deviation of considering each RGB bands individually and with the accepted values of RGB weights, this is the results that we got with improved standard deviation. And as you can see, the image on the right is of much better quality than the one on the left. Now Weber will take over.
So I'm Vaibhav. I'll be taking over from Mandeep and I'll be telling you about the future work that we have done. That is the video compression part. So before that, I'll run this on the terminal, the Quadtree formation, and I'll just show you how it works. So I've run the main.py, and as we told that this takes somewhat time to actually run, so it will take approximately 15 seconds to run. So in the meanwhile, I'll tell you what we have done for the videos. We have taken a 3-second video which has like 72 frames. It's a 24 fps video, and we have tried to actually convert every single frame into a image, and then into a Quadtree image, and then compress and combine the images back to make the video again. So here that program has run, and as you can see that the images now lost some of its clarity, but as you can see it is compressed now. So let me just quickly show you what we done with the video. So here as you can see that we have this videos frames which are like completely clear right now, and now we will actually show you the input video how it's running. So this is a 3-second video in which there's some trees and some clouds, and now I'll show you the video output video. And as you can see, after running the code through each of the frames and then combining back the frames, the video has been compressed to some quality, and it's still a complete video, but it has been reduced to some quality. So this is what we did with the video part, but as you can see that it took over 15 seconds to actually run for each of the frames. So it approximately took 15 minutes for us to compress the complete video, and that is an open question that we leave for future work on how to reduce that time. So in conclusion, the quadtrees are a very powerful data structure which we can use to compress images, and we are able to achieve some kind of reduction in the data size of approximately around 15%. And but there are some more limitations, like the image quality. Even if we restore the image back, there is some granularity. We're not able to exactly achieve complete accuracy, and we can try to improve upon that, but that would require us to go more into the depth of the tree, and that requires more computation power, and sometimes the an image might take even an up to a minute to be compressed completely. So if that happens, then a video which has like a 72 frames will take somewhat an hour to actually be compressed, which is like an unrealistic timeline. So we've tried to find a balance between the losing the quality of the image and the time it takes to compress the image. So that was one of the achievements that we were able to do, to have a middle point of this. So that brings us to the future work that we will try to improve the performance of the videos, and we'll also try to keep all the relevant info in the quadtrees itself, and ensure that the size of the images still remain on a decent level. Thank you.